Hey guys, today we are looking at section 10.4, rotation. So we're going to be rotating conic sections. So first, before we rotate them, I want to talk about the general forms of the conic section equations because those are what we're going to be using when we're rotating them. So the most general form is this one. Notice this BXY term that we have not seen any of the times we've talked about general form of a conic section. And that is because this BXY term only shows up if the conic section has been rotated. So if it's the normal one that we're used to seeing, then it's not going to have this term, only going to have this term if it's been rotated. So that being said, let's talk about what these different equations look like if they haven't been rotated. So if b equals 0, so if b equals 0, for an ellipse, we're going to have the equation such that a and c are going to be different, but they're either going to both be positive or both be negative. So you could have a -2 minus 3 here. And that would be an ellipse because they're different and both negative. So they're both negative or both positive. So that's what it means by a times c is greater than 0, right? If I multiply two positives together, I'm going to get a positive. If I multiply two negatives together, I'm going to get a positive. So they can either both be positive or both be negative, and they have to be different. That makes them an ellipse. If they're the same, then what you have is a circle, right? If A and C are the same, so if these are both 2, then I have a circle, right? So that's the only difference between an ellipse and a circle, is that in a circle, A and C are going to be the same. In a hyperbola, the difference is that one will be positive and one will be negative. Could be either one, but one has to be positive and one has to be negative. So that's why there's a minus here. One is positive, one is negative. So again, it could be the other way around, but one has to be positive, one has to be a negative, and that makes it a hyperbola. For a parabola, you're either going to have an x squared term or a y squared term, not both, right? If I have an x squared term, that's an up or down facing parabola. If I have a y squared term, that's a left or right facing parabola. So they're either going to have an x term or x squared term or a y squared term, but not both. And that would be a parabola. These hold true if there's no b term, if there's no, that xy term is not there. If you have an xy term, then you can use these rules to guess at what you think the conic section might be, but you can't actually be sure just by looking at the general equation. So in this part, the book gives just basically writes out what I just told you, except it's using the very general form of the equation. So instead of saying it's going to be an ellipse, it says it may be an ellipse. So if A and C are non-zero, have the same sign, and are not equal to each other, then the graph may be an ellipse. So if you have the BXY term, you can guess at what you think your conic section might be, but you can't actually be sure just by looking at the equation. And this has, again, all those rules written out. So let's look at this example. In this example, we're given all equations that don't have that b term. So we can be sure which conic section these are. We don't have to guess, we can be sure. In this one, we have a positive term and a negative term. So this is a hyperbola. In this one, we have only one squared term. So this is a parabola. In this one, we have 3x squared and 3y squared. They're the same, so this is a circle. In this one, we have a negative 25x squared and a negative 4y squared. They're different and they're both negative. So this is going to be an ellipse. Okay? So both negative, ellipse, one positive, one negative, hyperbola, only one squared term, parabola, same is circle. Notice I'm not even looking at the rest of the terms. The rest of the terms play a part. They're going to change the size of my conic. They're going to change where it's centered. But they're not going to change what type of conic this is. We only need to look at the squared terms to tell what type of conic we have. Again, none of these have that xy term. If we have an xy term, then we can't say with 100% certainty what conic we have just by looking at the equation. Okay, let's move on. So this is what a rotated conic looks like. This is specifically an ellipse, right? So notice in the equation, we now have an xy term. So this is an ellipse that has been rotated a certain number of degrees. We don't know how many, it just says theta. So it's been rotated by theta. So we have now sort of, you can think of it as having a new set of axes, right? They call them x prime and y prime. So you can think about it as this is an ellipse, the same ellipse on a different set of axes now that it's been rotated by theta. So the axes themselves, you can think about them as being rotated by theta. So we're going to talk about how we can represent our new our old ellipse in terms of our new axes. So getting this equation in terms of x prime and y prime. We're going to find equations for that. That's down here. So we want to get things in terms of x prime and y prime. So if we look at this diagram, and we've talked about this back when we talked about did all that stuff with our unit circle and our sines and cosines. If I have this theta here, then this distance is going to be sine theta times this distance. So when it was a unit circle, this distance was always 1. So this was just sine theta. But if this is not a unit circle, then you have to multiply by this distance. So this distance times sine of theta would give me this distance here. And then this distance times cosine theta would give me this distance here. Okay? And then if this is theta, because right, if we shifted the x-axis by theta, then we've also shifted the y-axis by theta. So now sine and cosine are switched because theta is up here instead of down here. So this is cosine theta. So this would be y prime cosine theta, and this would be y prime negative sine theta. So negative y prime sine theta. So this is x prime cosine theta, x prime sine theta, negative y prime sine theta, y prime cosine theta. That's a mouthful. Okay, I'm going to start writing things down. They have a whole proof of this further down using vectors, but I'm going to do it a little bit different way. So if you think about it, the x distance that I have gone, if I shift my axes, right, and I go a certain x prime distance, the x distance that I've gone is x prime cosine theta and negative y prime sine theta. That's the x distance. I've done both of those things. I've gone this way and I've gone that way. So x is going to be x prime cosine theta minus y prime sine theta. Okay? So I'm taking into account both of the x direction movement, because even though this is now sort of our new y-axis, because it's not actually facing the direction of the y-axis, it now has an x component as well. So I have to take that into account when I'm figuring out what my x movement has been. So then for the y direction, I've gone x prime sine theta and I've gone y prime cosine theta. So y is going to be y prime cosine theta plus x prime sine theta. So with x, you have this minus, and with y, you have plus, and the sines and cosines switch. You don't need to memorize this, but it'll help you to kind of know it, be familiar with it at least. So looking back at the slide that I went down to a minute ago, it has that written out, right? X prime cosine theta minus y prime sine theta, and then x prime sine theta plus y prime cosine theta. They wrote it in the other direction than I did. Doesn't really matter. Same thing, right? But yeah, so the x is the one with the negative, and then the y has the plus. All right, so hold on one second. All right, this video is getting a little long, so I'm going to stop here and we'll do actual examples in the next video. Let me know if you have any questions, and I will see you later.